We have basically discussed very simple solutions of the wave equation. D'Alembert and then okay, let's remember, right? Okay, what about this? That's boring, if you remember. It's really boring, and it's this. Boring. Good. Now, when we want to deal with realistic waveforms, for example, acoustic ones, like the ones that we are going to produce, that we are producing when we talk, or when we sing, or when nature is making some noise, waveforms are much more complicated. So they don't last from minus infinity to plus infinity in time. They don't have just one frequency. But we can imagine that they are made by packets, like words, like transients, like this or this. So the waveforms appear much more complicated. Now, can we use this solution? Yes. Actually, we do every day. For example, any digital player actually is creating sound, adding harmonics. If you remember, during the last lecture, we have played with strings, with boundary conditions. We decided the length. Then we found that the length is deciding the wave numbers that now are discrete. Velocity is deciding frequencies. And since the frequencies are multiples of a basic one that we can call fundamental, we call that harmonics. Okay? And if you want, one harmonic is given by one frequency. Good. What about these more complicated waveforms? Well, actually, what Fourier told us, and it was a sort of a revolution, his findings occurred just a few years later than the French Revolution, so it was during the Revolution. He was visiting Egypt with Napoleon, and he was studying heat transfer. You do know that heat transfer is not following a wave equation. For conduction, it's following diffusion equation. But actually, it's a sort of a disordered wave system. Okay, so he was thinking about how to write the solutions of the heat equations. And he was thinking about, okay, can we use simple solutions? What is simpler than this? Nothing. That's the simplest waveform signal that we can imagine. And so he proposed his paper to the French Academy, and it was really not accepted at the beginning. It seemed impossible that complicated functions can be written using this. But actually the idea is very simple. You can treat a complex waveform and decompose it in very simple ingredients that are called frequencies, or if you want, harmonics. So you can do an analysis, or vice versa. You can consider these ones to sum them and create a complex, but that's called synthesis. And the idea is just here. If you properly sum with the proper amplitudes a function, a wave function harmonic and its multiples, okay, you can create whatever function that you can imagine in that period, of course. And you can extend to infinite period of signals.
Did you press it?
I did it.
Yeah.
I hope. It's blinking, okay? Thank you. So, what about terminology? The basic break of terminology is just one harmonic. In sound, you can call that the pitch. But pitch is a technical word that is how we perceive frequencies. So for example, you can call a frequency of 220 Hertz. What we hear is the pitch of 220 Hertz. So you have seen, you have felt how energy, power, intensity can be mapped in decibels. The perception of a decibel is called loudness. The perception of frequency is called pitch. But you can use that as a sort of a synonym of frequency. But what is important here is harmonic. So multiples of a frequency that is the base frequency. Okay, what about this mapping? But if you want is going from the time domain, and actually this is what we're interested in, for example, listening to sound, or looking at a seismogram, that is a transient, that is a waveform, and can we map that in another domain that we call it frequency domain? Well, the representation, the typical representation in acoustics is like this one. So we have an axis that is a frequency axis, and it is running from some specific values. For example, in acoustics, it's running from 20 Hertz to 20 kilohertz. Why? Well, because that's the frequency range that we can listen to. What about amplitudes? Okay, in acoustics, the typical amplitude is in decibel. It means, okay, that frequency is there with a given amplitude. You do remember that decibels actually are 10 times the logarithm of I, that is an intensity, that is related to power, that is related to energy, that is related to an amplitude, over a standard intensity, 10 to the minus 12, in our case, watts over square meters. Good. So, the typical representation is this one. This is valid for acoustics. Why? Because our apparatus is not sensitive to phases. But actually, you do know that when you map something like that, you need an amplitude, okay, it's fair. You need a frequency, okay, it's fair. But actually, for a general sense, for transient, we need also to take care about a phase pair. And you can also imagine to break the exponential function using the Euler's formula with cosines and sines. It's totally equivalent. So the typical representation is something like that. It's squeezed. You see, sines and cosines, or magnitude and phase. What is magnitude? Well, it's the amplitude. What is phase? Well, it's deciding if it is a sine or a cosine. If you want to hear it, and if I change the phase, our perception is not changing. But physically, it's moving, of course. If I change the amplitude, yes. It's not working, but okay. It should be louder or softer. Now, that's one frequency. What if we had another one? Okay. What about another one? You see, if you take the cursor and you move it, you see the different components. Okay, that's enough. Oops. So, actually, it's like Fourier theorem is like a recipe, a cook handbook. You have the ingredients, frequencies. You want the final dish, okay, and Fourier is telling you how to cook them. Now, what was the original idea? That's the final representation. But actually, when you sum harmonics, you have to say, okay, what is the frequency and what is the amplitude? And then you sum them. It's a linear combination. Nothing more, nothing less. And actually, you can imagine as a table of a recipe, or you can imagine to take the table as a plot. Frequency, amplitude. okay? And you play with this. Playing with this, you can create new functions. Vice versa, if you have a function, you have to look for the ingredients that are there. So, synthesis and analysis. What about the final typical representation in acoustics, but now it's valid in many time series analysis? It's called spectrum. What is that? Oh, well, actually, we have seen it when I was playing with my app of a mobile, and I can also use it later. It's nothing else than a frequency analysis, a Fourier analysis, running in time. It's very important in acoustics, for example, because you can analyze the different frequencies that are, for example, inside speech, or how you pronunciate vowels or consonants. If you think about it, for example, consonants are much more rich in frequencies, like T, S, F, something like that. Every language has its own consonants, but all of them share the same common feature that they are very rich, very noisy, while vowels, actually, A, E, I, O, U, have a different, how to say, emission and a different spectrum. And usually they are decided by what we call formats. By the way, that's acoustics, but in general, what you can do is to take a time series, to compute, to analyze it in the frequency domain, the Fourier domain, and to look in time how it is evolving. It's very important also for seismic signals, okay? Because you will see from the next lecture on, we will begin the study of elasticity and waves in the Earth. You will see that a seismogram is much, how to say, is very rich of informations that we can use to start a tomography, for example. And it is made by different waves and different physical phenomena, for example, body waves, surface waves, dispersion, stuff like that. And so a spectrum can be useful to analyze the different features inside a time series that can be very, how to say, complicated, complex. Okay, that's not a picture, but it's a portrait of Fourier. And actually, his theorem is very simple. That actually you can write an x of t simply summing sines and cosines. Or, if you want, amplitudes and phases. I'm using in these slides here the double feature of amplitude and phases and cosine and sine, because please remember they are totally equivalent. Okay? Now, you cannot see here, but it's 18 something. It was the beginning of the 19th century, so it's not a long time ago. And it was based on a theory of heat, but actually his solution can be used for whatever function. I would say that the most important application is in wave physics, so analyzing waves. Okay, what is the trick? Here I'm using the other version, cosines and sines. What is the idea? Okay, if we want to write an f of t, or if you have an f of t and we want to see the ingredients, the trick is to look for the a's and b's, or capital A's and phases. How to do that? Well, actually what Fourier used and what we are using is simply the concept of orthogonality of the base functions. So it's only a matter of solving integrals. For example, what about the first term? Actually, it's the average of the signal. So if our signal has a zero average, like a transient, so something is zero, something is moving, then going back to the equilibrium, the first term will be zero. What about the other ones? Well, what you have to do is to take the function, multiply it for the different cosines, and solve those integrals in that period. You will get a recipe to look for A's and B's. Vice versa, you can take F, analyze it, or if you want to build F, you can use these A's. It's a sort of a dual vision. So an f of t can be mapped in terms of frequencies. It's the typical Fourier analysis. It's a decomposition. Actually, it's only based on completeness of a base system. So, sines and cosines can be used as a base for a function. You have a periodic function of the period t, the game is over, because you take this as a fundamental frequency and you go for the other ones. You project that function in that domain. There are some nice examples. I will show you just one that is very simple, and it is related to a square wave. Okay, you see, well, a square wave is simple, but it has corners. It's not a beautiful sine or cosine. Well, just using intuition and no algebra, you see that the period of a square wave, it's given. And you do understand that it is starting like that. The basic brick will be a sine with that period. Now the idea is, okay, can we use other functions to model the corners? The answer is yes, if you have enough time. Because actually, in principle, you should use an infinite summation. But for lazy people, you can truncate it and say, okay, it's acceptable. This is in everyday's life. Now, what can we do here? Well, we have a function, and we want to find the ingredients to be cooked to find that function. Okay, it has a period here, for example, a period of 2. It's 1 or minus 1. If you think in terms of intuition, the average is 0, so the first term will be 0. What are the basic functions that we need in this case? Well, sines, it's evident, and no cosines. Actually, this will arise also from algebra. For example, what you can do is to compute the integrals. Let's compute the first one. Well, first is 0. Easy. What about the other ones? Well, let's give a look to the cosines. If we project the f on the cosines, the shadow will always be 0, as it's coming out from this algebraic property here. So all the a's are 0. What about the b's? Okay. Very simple algebra. You project now the function over the sines, and what you find are the necessary amplitudes that we need to use in that summation. And you can find this general expression. Okay, and we can rewrite it in different terms. Okay. Now, what about the first one? It will need to have this amplitude with n equal 1. Then with n equal 2 is not there, then 3, then 0, 4. So you have a recipe. Now, do you want to see it here? Let's be square. Now you see the first, we can give a look in magnitude or sines and cosines. So this is taking the largest contribution. You see, if you put the cursor here, you see how much of this do you need. Now you have a little bit over and you have a little bit under here. How to compensate? Well, now the other terms are needed to change it. If you sum them, well, this is what you get. You can say, oh, wait a second, that corner is not perfect. Yes, because maybe you need other terms. And you have to be less lazy, but it's a very good approximation. You see how the contribution of the higher terms is getting smaller and smaller, because the general expression is this. Okay, that's Fourier. And now, what we can do is to listen. It's not that nice. Now, what is this? We don't like that sound. But actually, if you would take this one, it's the old 220 that we were listening before, but with higher harmonics that are giving the timbre of this sound. What if we change some amplitudes? Well, you see that now the signal is changing. You see how the recipe is very accurate. If we change a little bit, it's no more that one. Now, what if we change phases? Well, let me go back to this. Okay. Now, if we change the phase, you see that now the signal is changing. Maybe we don't listen to it. So in the acoustic domain, we can change some phases, but we're not listening to it. But in the time domain, it's changing. So please remember, phases are important. Not in acoustics, but in the other domains, yes. Can we do something else? Yes, we could do for many other examples. For example, a triangular wave. What is the most important contribution? Well, this one. Actually, if you play it, it's very similar to this one. What about this? Oh god. You need higher harmonics with this one. So, strongest the corner is, higher is the number of harmonics that you do need in the summation. That's the trick. What about noise? Well, noise is, it's not easy to define noise. In acoustics, maybe it's easy. That's not so noisy, but it's something that is not signal. So if you want to speak with someone and other people is chatting somewhere, that's noise. Or if we want to listen to some music and someone is speaking, that's noise. Or if you want to speak and there is some music, that's noise. So it's very subjective. But in general, you can define noise, something that has a random spectrum. So all the frequencies, but mixed. Then you can define some white noise, pink noise, red noise, but noise nowadays is not easy to be defined. For example, in seismology, noise is something that is not related to the passage of wave, of a seismic wave, but actually noise that can be caused by cars, humans, or nature like wind. Actually, that's noise because it's not a wave coming from an earthquake, but in many cases now we're using noise as data and we're excluding earthquakes. So it's not easy to define noise, but for today noise is something that has a random spectrum. So it's not ordered like this one. This has a very specific recipe. This has not. Okay, now let's try to conclude this part. So, with some algebra, what you can do is to find the recipe for whatever function. This is the case of a square wave that you have just seen. Okay? Can we use that? Well, as I told you, we use it every day. And let's see if I'm able to for example, now I'm using this microphone here, and you see the Fourier spectrum, that wiggly curve. And if no one is speaking, there is something. That's noise. And it is there. If I'm speaking, you see the spectrum is changing, so if I'm saying A, E, I, O, U, the spectrum should be, it's not that evident, but you see that these patterns of amplitudes are changing. That's a spectrum. So, frequency, amplitude, and time. So we can use it for reproduce music, like an MP3 player or any digital musical player is summing harmonics. Digital radios are using this. We have the frequency generator in our devices that are reproducing something that we say, oh, someone is speaking, oh, there is music. It's based on this. Because it now can be done in a very fast way. Actually, it can be done in no time, as you can see. Okay, what I want to show to you is another application that is going to close our introduction to vibration and waves, and it's going to conclude the string. We're going to use next the string as a sort of a paradigm to understand the Earth. Okay? Now, we have a string with its length, with its tension, with its linear density. And now we know that given those, parameters, wavelengths and frequencies of the normal modes of the string, they are given. They are just related to the system. Now, what about the player of a string? Well, the player can decide initial conditions. So I can take the spring and plug it here, or here, or here, and release it. What's going to change? The sound. Because then the initial condition is going to decide which frequency will be excited most. So a system has its own modes, but the player can decide which ones to play. Can we represent this? Yes, using Fourier. But not in time now, but in space. And actually, you use Fourier analysis in space every time that you play with filters on pictures. For example, if you take a digital picture and you want to filter it, you're using Fourier in space and not in time, in 2 dimensions. What can we do? Well, the initial profile of a string will be a function of x from 0 to L. That is a function. It should be a polite function. We don't want to break the string, of course. So that profile is an f of x at t equals 0. Well, let's write it in terms of harmonics. But the harmonics now are not in time, but they are in space. What is the fundamental brick? Well, it's the fundamental mode. Then the first diode, the second diode, the third diode, we have infinite. So according to the profile, that maybe is a very corner, it's showing some very rough corners here, well, we will need to add higher harmonics. But what we can do is to take that function and to write it in terms of this. The modes are given, the A's are decided by the player. And they will be decided according to the initial profile, so where we decide to play the string. So if you write that function in terms of Fourier, what we have to do, given the initial condition, is then to write the solution. And any harmonic in space will have its own frequency. If you want, these are the eigenfunctions, and these are the eigenvalues. So once you fix the string, and you do the beautiful plot that I told you, please remember it. Once you decide the length of a string, lambdas are given. Full stop. Once you decide tension and density, frequencies are given. What is not given is the relative amplitude of each of them. Initial conditions, the player, or in the case of the Earth, for example, an earthquake. Okay, so you see, that's one of the most important expressions in physics. You can write a function over a string inside a system, properly summing its normal modes. So if you remember, we started the course with 1 degree of freedom system with just one frequency, mass and spring. When we put together 2, 3, 4, 5, 6, 7, we added the number of normal modes. Now we have infinite. Why? Because we have a continuous distribution of mass here. We can take derivatives. We can decide what is a linear density. So that's mu. So from now we will turn into more complicated systems in solids with boundary conditions. And I hope that the final lecture of this course will deal with a similar expression but for the Earth. It will be much more complicated because we don't have just one dimension, we have three. It will be a sphere. Well, you can say it's not a sphere, but well, okay. For lazy people like me, yes, it's a sphere. So 3-dimension, spherical geometry, and it's not homogeneous. So we don't have just one velocity. We have different materials inside the Earth. Okay, but that expression will be generalized for the Earth. But today, after looking at that applet, we will go back for less than 1 hour to the discrete nature of a real string. So if we use a lens, a nanolens, we could say, wait a second, that system is not discrete. We have atoms there. And we will find a surprise there. But this will be after looking at this. By the way, let me show to you just some very simple acoustic examples. This example here, well, this game here was just about changing phase. And the experiment here was that changing the phase, we will not hear it. Okay, I've already shown in an acoustic sense to you. What about this? Well, you will hear first the sound created by a clarinet. Then higher harmonics will be removed and just the fundamental will be there. And you will hear that actually if you remove the harmonics, the timbre of a sound is totally anonymous. So let's try, let's see if it is going to work. Clarinet, just fundamental. The second part could be emitted by whatever instrument. It was the higher harmonics that you see here, that's the spectrogram, are creating the full timbre of that sound. You can say, oh, that's a clarinet. Let's try to hear it. Let's. In the time domain, that's the situation. The full waveform and just the fundamental. You see how a pure harmonic is not only boring, it's useful, thanks to Fourier, but actually has no personality. So when you listen to a musical instrument, for example, is the richness of a spectrum that is giving its own timbre. Okay, that's why I put these slides here. Let's visit this applet that I already discussed with you, but now maybe you will fully understand it, I hope. It's the loaded string applet. What we do have here is a string with its length. What are the parameters with which we can play here? Well, for example, damping. Damping here is pretty much 0. But please do remember that any realistic system has some damping. Does it mean that the Q, and we studied it, is not infinite? So sooner or later, the sound is going to stop. Not only because it's going to be propagated, and geometrical spreading will take part of the amplitude, because it's going to be generated on wider areas, but also because part of it will be removed by damping. So here you can decide the damping, or you can decide to play with the tension. Now, what about the tension? It's going to increase the restoring force it's going to increase the velocity, it's going to increase the frequency that you can hear. What's next? Well, what we see here are the different modes that we can play. Let's be fundamental. Let's be first. Oops, sorry. Well, you can imagine you can play with all of them. Also with very wiggly ones. What now if we play the string? Now, if I do this, I decide an initial profile. That profile can be decomposed in Fourier. And we are deciding now the amplitude of the different modes that we're going to play. So you see, according to the position, look at the amplitude of the modes later. You see that they are changing. For example, if I plug it in the center, the most important contribution will be this. Now, what is funny is that actually, when I plug it, I'm generating progressive waves. Let me try to go very slowly. Now, this wave is a progressive, but it is written by standing waves. Which ones? Well, this and this. Not this one. Why? Because this one has a 0 where I was plucking a string, so I'm not exciting it. So all the eigenfunctions that have a 0 at the initial plucking point, well, they will not be excited. Now you see, these are still progressive, but they are written in terms of this. Oh, that's very slow. What about the sound? But if I play it here, it will be richer in harmonics. Progressive waves written using standing waves. If I diminish here the speed, oh my god. Progressive, going reflected, but they are written using this, this, this. What about the damping? Well, the damping will decide how the shape will be deformed and then ceasing, going to 0 in time. That's too damped. This is not damped. Progressive. I never try to. Let's see if it is. The sound is changing. Yes. Okay, so just to recap. This applet here is showing us how the initial conditions are deciding the different amplitudes of the modes of a system. Those modes can be used with the proper summation to write progressive waves. Modal analysis, if you want. But remember that physically, the standing waves actually will be generated later by the interference of progressive waves. So physics and mathematics. Okay, what's next?
We know the velocity is proportional to the tension. So if you increase the tension, then you should increase the velocity. But why is it that when you decrease the tension here, then the velocity was a bit higher?
Velocity of what?
The strain.
So,
I could see from the movement.
oh, this is faster.
Yeah. Okay.
Oh, this is lower.
Yeah.
Velocity of progression of waves. Do not mix it with velocity of vibration. They are related, but they are not the same. Okay? Okay, what to do next? Well, what we can do now is to go back just a little bit to this system here. Why? Well, because it will be the first example of a physical phenomenon that we are going to meet when we will discuss surface waves in the Earth. And in this case, this phenomenon will arise from a totally different system. Okay, recap. We have already seen the first 2 slides of this set. And we discussed them when we had been coupling oscillators. 1, 2, 3, 4, 5. And now we can imagine that those balls are representing masses, but they're not free masses. They are atoms in a lattice, and there are some interatomic forces that are connecting, like springs. What about interatomic forces? Well, they follow this potential, for example. That's an example of interatomic potential. What can we do with that potential? We could say, oh, some quantum force, some Coulombic force, we mix together and we have that messy function. Well, it's not that messy because we have a minimum there. What can we do with that minimum? Well, we can say every time that in a potential there is a minimum, we have a stable equilibrium. If we have a maximum, we will have an unstable equilibrium. And the system, once it's moving from that equilibrium, is going to run away from that. In this case here, if we stay there, okay, and if we perturb the system, it's trying to go back. So, we stay in the neighborhood of the minimum, we use Taylor expansion, and we try to be lazy. So, the first term is the amount, how much is the potential at the minimum. The first derivative is 0 because it's a minimum. The other important term is this one, and it is quadratic. It's a parabola. Okay, if we have a parabolic potential, if we compute the force, it will be minus kx, Hooke's law. So every time that we have a stable equilibrium, and we truncate, we see in the neighborhood of a stable equilibrium, we will have a parabolic potential and we will have a linear restoring force. And that's the basic ingredient for having a periodic oscillation and then a wave system if we couple oscillators. Let's recap of the course. Okay, parabolic potential, forces. What to do next? Okay, let's represent the forces, for example, in terms of mechanical springs. Okay. What about the strength of a spring? Well, it's representing the strength of a potential. For a gas, for a liquid, for a solid. In the case of a solid, it will be stronger than in the case of a gas. Okay, so we can write for every element of the system dynamic equations. And now Hooke has to speak with Newton because the dynamics are ruled by acceleration. If we have forces, we have acceleration. The mass is given by the characteristic of the atoms that we are considering. The single acceleration will be related to the forces, and they are related to the position of the two neighbors and to the relative positions. That's why it's a coupled system. Okay, so we have to write for every element of the system an equation like that, where we have the position and the position of the previous and of the other one. Okay, now, this is the new part. Until that one, we studied it. Now it's time to revisit it with just a very simple idea. Now, let's take that lattice. We have it. It's a necklace, if you want. And we can imagine to perturb it. Maybe in a longitudinal way, sound, compressions, rarefactions, or maybe in a transverse, like in a string. By the way, what happens if now we take that lattice and we inject there an harmonic function? Like a wave. What's happening there? Let's give a look to it. So we have a solution here that is very similar to a wave, but wait a second. X is not a continuous variable. It's discrete. Because between the atoms, we cannot define space. So that's why here, position has to be one of a position of the masses. Okay, that's the difference. That's the only difference between that system and a string. A string has a continuous distribution of mass. Okay. It's time to do some very simple algebra. You plug this solution in, you get this. Please give a look that the space is defined just in discrete positions. Now you take this one and you cancel this factor. Now what is A? Well, that's the most important parameter. It's the distance between atoms at the equilibrium. Okay. How much is A for a string? 0. Because the distance between atoms is not seen by us, okay? We live in a continuous world. But if you take a length, A is a given, for example, 1 nanometer. Good. Now, if we plug into the system this solution here, we are getting this. Wait a second. Because now, omega has to be described by this function here. And that's why we are discussing this system, because you see that there is a magic word there, dispersion. And we will speak today about dispersion. We're speaking now about dispersion. That is a phenomenon that can be described in many ways. For example, the typical example of dispersion is when you take a ray of a sun, light, you use a prism, it enters, and is beautifully spread, and you can have rainbow with this rainbow. Why we do have rainbow or white light is separated in its components? Well, actually that's Snell's law. You remember Snell's law? Otherwise I have a tutorial, but just in case. But for today we will use the idea of Snell's law. Refraction angle will be dependent upon the velocity. Velocity of a white light in the air is constant, but inside the glass it's not. It depends on frequency. And so, the refraction angles for the different components of a white ray are separated because they have different velocities. And we can admire rainbows. So, when velocity is dependent upon frequency, we have dispersion. There is another way to describe it, and it is written here. Now, give a look to this. I told you that this is maybe the most important expression of this course. And it is coming from a very simple one. They are the same. Now, what about the relation between omega and k? Velocity, up to now, is right? What about the velocity of sound and of transverse waves? in a string. There is no frequency here. Am I right? It's not frequency dependent. What does it mean? That the plot is a beautiful straight line. Whatever the frequency you plug inside air or a string, velocity is not dependent by frequency. So there is no dispersion, right? When there is no dispersion, in the omega k plane, we have a straight line. Whatever frequency you consider, whatever, because velocity is constant. That's until 5 minutes ago. Now look there. What is the relation between omega and k? It's not a line. That's why it's called dispersion relation. What do we have here? 4 number. C, it's a constant. M is given by the system. A is given by the system. But if you take omega and k, what you see here is a periodic plot. It's not a line. Okay, this plot here, that is very simple and can be derived by very simple algebra, is called the plot of Brillouin zones in solid-state physics. But maybe we don't care in this course about solid-state physics, but we're just giving a look to a discrete system, and due to its discreteness, it's giving us this instead of this. So bad news. Should we throw away what we have studied until now and what we're going to study from Friday on? It's a question to you. No. No, because we don't want to lose what we did until now. And we are not so silly that we are going to speak about nothing. Is there a way to find something useful there? Oh, for solid-state physics, that's life. Because A, that is, let's say 10 to the minus 9 meters, it's important. What about sound and seismology? Well, we don't see 10 to the minus 9. Our vibrations, our perturbations are much longer than this. We don't see those walls. We can sit. We can sit on the chair, I can stay on the table, we can walk on the pavement. Where is our world in that picture? That's my question. In this one. In this picture here, we can work. We have been working and we will work.
Reciprocal nature, reciprocal nature.
No. Let's try to be lazy. Let's take the sine and let's take the shortcut. Now, if you write the sine in terms of the first element of the series, when the angle, the argument is very small, you can take just the argument, right? We did it for linearize our equations, if you remember. Now, let's imagine that we take just the first term. Okay, Ka2 is coming out, 2 is a number, and now we have 4mCAK. It's a line. If the argument is very small. Now let's give a look to the argument. It's Ka. What is Ka? Well, when this is small, when the wavelength is much larger than A. So actually, for every perturbation that is much larger than 10 to the minus 9, and 1 meter is 9 orders of magnitude larger, actually this is very, very, very small, and we get back this. And what it is? Here. So actually, if you take this part of a word, that's our word. The word of continuum mechanics is here. Because Ka is A over lambda, and what does it mean? That now K is going to 0. And actually, if you take that sign, that's a line. So actually, this picture here is showing a beautiful example of dispersion. Why? Because omega and K, they are not lines. It's not a line. But it's like if this line here is put like that. By what? By discreteness. But if you stay very near here, that's continuum mechanics. Remember, whatever is larger than 10 to the minus 9 is continuum mechanics. So only when the wavelength is comparable to A, that is the step between atoms, you feel this. Solid state physics, not classical physics. So you can relax. I can relax. We have studied sound waves, and they are here. We are going to study seismic waves, they are here. But if you want to study solid state physics, you have to remember, oh, wait a second, between omega and K, there is not a linear relationship. We have a periodic one with signs. That's why it's called dispersion. Because every time that omega and K is not a line, this is a prequel, d omega over dk is not a line. And what is this? It's called group velocity. We're going to study it. So every time that omega over k is different than this, you have to speak about phase velocity and group velocity, and you will have dispersion. That's another way to describe dispersion. So it's the first time that we listen to this word, and we're going to listen to it, but in a totally different case for surface waves in the Earth. So please do remember, this is one example of a phenomenon that is saying that according to the frequency, velocity is different. Because actually, you see here that if you plug inside the system a very low frequency, well, it's more or less a line. It's like sound. But if you increase the frequency, you cannot go over here. Those frequencies cannot propagate into the system. What's going to happen? Your homework. But you can relax because the answer is later in this slide here. But you have to think about it. What's going to happen to frequencies that are higher than that cutoff? You can inject them into the system, but they are not going to propagate. And the tricky way to describe them is here. It's your home. Because, okay, let me answer for you. Let's imagine that K is imaginary. I times I is minus 1. And so K cannot propagate. They are damped. So all frequencies that are higher than the cutoff frequency, you can inject them into the system, but they cannot propagate. They are damped in space. If you want to use a beautiful, sophisticated terminology, you can call them localized phonons. But it's nothing less or nothing different than a damped vibration. Who decides this cutoff frequency? Well, this. It's the mass of the atom and C, that is the constant that is relating the strength of a spring that is representing interatomic potential. It's given by the system. Now, can you imagine, and we're going towards the end of this part here. Can you tell me, using just intuition, why we have periodicity there? You see, it's periodic. It's the sign. In classical continuum mechanics, we have an infinite line going over. It's not periodic. But there, we have to come back. Can you guess why?
The restoring force between the particles.
Let's imagine that we have a string. We can wiggle it how many times we do want. But actually, sooner or later, if we go to very small wiggles, we will realize that between 10 to the minus 9 meters, there is nothing. We cannot stretch that part. So sooner or later, we will see the discrete nature of a string. Now, here, we cannot do, the game is over. So once we feel all the possible vibrations of that system, we have to go back again. Let me show to you an image that I hope I will put here. Okay. The final animation is, please forget it for now. Look, let's take an example of 5 masses. And now we apply a boundary condition to our necklace. If you do remember, we treated this. Now let's take 5. And let's try to play like in the classical string. Okay, fundamental mode. First higher mode. Second, third, fourth. Okay, that's the end, my friends. So lowest frequency, first higher, second, third, fourth. Game is over. Because if we inject higher frequency here, we go back to this one. Higher, go back to this, and so on. We have no more space for our fantasy. Because inside those masses, we cannot put other things. So once the frequency is over, it has to go back to other configurations that are the same. You cannot distinguish this by this and by this. Why I was putting that animation downstairs? Because actually it's related to what we call aliasing, or Nyquist frequency. If the frequency of your information is too large for your sampling, you don't see it. And actually, this red, wiggly sinusoid is seen as the black one. And actually, the black one is not there. But since you're sampling the red one at a too low sampling rate, you see the black, but the reality is red. It's like aliasing. What I want to say is that every time that you go to a discrete system, you will get a cutoff frequency. Because after that one, look, classical string. Now, once you have the lambdas, you have a case. So please, let me show to you the final. That's why usually I prepare these 2 slides together. Not this one, but this one. let's make a recap here. Classical string. Length is giving lambdas. Okay? If the boundary condition that we have chosen is fixed, it has to be like that. It has to be a sign for the boundary conditions. And Kn has to be, if you do remember, I've been writing it. What does it mean? Kn is discrete. These are the modes giving exactly this. Because actually, if you write k as 2 pi over lambda, you will get this. Okay? Good. And that's why we can write the full solution of a classical string. This is too big for. Okay? So if you write the solution here, you can take the k's here, whatever. You can increase them. Pi over x, 2 pi over x, 3 pi over x, you increase the lambdas, right? And you get smaller and smaller wavelengths here. You can do whatever, n can go to infinite. Wait a second, because sooner or later that lambda will fill the discrete nature of the string. So actually, there is a limit, the interatomic distance if you want, and the lambda cannot be smaller than that. But in the classical theory, yes. But in the discrete system, it cannot. Now, let's give a look to this. Oh, let's stop it. That's the, what is it? This is the lowest k that you can imagine and the largest lambda that you can imagine. Then you increase it. You increase it. Now lambda is getting smaller and smaller. You decrease it. You decrease. Oh. That's the end, my friend. You cannot go less than that. If you go less, if you increase your kappa, you're getting this, you're getting this, you're getting this. You see, now lambda is smaller. But look at this. Here, you're making one full period between this and this. But this situation is exactly like that. And you can increase it. But you will not see a difference there. For example, you can put this, 2 cycles and half. But there is no difference between this, this, and this. You don't see it. So, to sum up, in the omega k plane, when you go to the discrete nature, you increase kappa, so you decrease lambda. Remember, kappa is 2 pi over lambda. You start from k that is going to 0. What does it mean? We're writing it, okay. So, very large lambdas. You increase kappa, you decrease lambda. Sooner or later, you're going to fill it, and that line cannot be a line anymore. It's going to be a sign, whatever, because you can plug there the smallest wavelengths that you can imagine, but there will be no difference. So periodicity of a dispersion actually is related to the fact that between this point and this and this, you can put whatever, but you don't see it. Okay? And this is giving out this picture, that is not a line. But, as I told you, wait a second, all the theory that we developed for strings, classical ones, and sound is still there, but it is here. When k is so small, when lambda is so big, that we don't feel A. Now, A, for every application in the Earth, is nothing. Because we are working in the smaller scale with frequencies and wavelengths that are not less than 1 centimeter. So we don't feel A. And we can live in a world of classical continuum mechanics. But what is funny is that if you remember that there is an A there, you got this picture and you got dispersion. Why dispersion? Because omega and k are not linearly related. And so, we can have what we call group velocity. In other words, omega over k is velocity, but there is also another one, the omega over decay. And if you compute it, and you call it group velocity, you're getting this plot here. Now, that plot is actually part of your homework. So in 15 minutes, I'm going to send you an email with 3 very simple questions. And part of the answer is there. Now, please give a look to the curve of what we call group velocity. What do you notice? It's starting from a value and then going to 0. Now, the value with which you're starting is actually equal to what we call omega over k, that is phase velocity. Now, let's imagine, now that's the sine and that's the line, okay? If you stay here, when the sine is pretty much the argument, classical mechanics, classical continuum mechanics, you see that if it is a line, omega over k is practically the omega over dk. It's the same value. Later, omega over k is a number, but the omega over dk is another number. So every time that the curve is not a line, the two values are different. And here, on the top, the omega over dk is 0. Now, as you can see here, that value and all the other ones where the omega over decay is 0 are actually the configurations of the normal modes, but seen in the discrete world. And normal modes, we call them standing waves. Right? Progressive, standing. And I told you, in a progressive wave, there is a net flux of energy going with the wave. In a standing wave, there is not, because energy is localized in the maxima and 0 in the nodes. You do remember? So there is not a lateral flux of energy. Group velocity, the omega over decay, is the velocity of energy. And when it is 0, energy is not propagating, it's standing. That's why this is a very simple but beautiful example of dispersion, where omega and k are not linearly related. Omega over k and d omega over dk are different. And one is called phase velocity, the other one is called group velocity. And group velocity is the velocity of energy. You're going to think about this for your homework. Let's conclude this part with this image here, because now we can see another way to play with boundary conditions. For example, let's give a name to this system. It's a system of n masses, right? Since we want to be very sophisticated, we can call them 1D lattice. It's a name. It's the name given in solid-state physics. Okay? Vibrations of monatomic 1D, lattice. Its vibrations, they are called phonons. It's just a name. What is important is that phonon is coming from ancient Greek, from phonos, that is sound. Because actually, these are like sound waves, but in a discrete set. So vibrations of monatomic 1D lattice that are called phonons are nothing else than the discrete microscopic or nanoscopic version of sound waves. And if you take now our string, we should say, okay, let's take, for example, I don't know, some masses here. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a number. Could be 2, 3, 4. Okay, we play with that. We can play with boundary conditions. For example, we can say that this one and this one is fixed, or one is free. 2 are free. We played during the last lecture. Or in some cases, solid state physics people is simply putting another boundary condition that is, okay, this one is joined with this one. It's a nice way to go to infinite. Okay? So you say the displacement of this one is this. You can play whatever, but once you have a finite number of masses there, you can find some configurations where you put all of them on one side of, and so on, until you go to the end. Because now you cannot wiggle them with a finer wavelength. That's why after this picture I was putting this one. Okay? It's nothing else than the discrete version of a string. But the news are related to dispersion. And this is the topic that I want you to go deeper with the homework. In the homework that I'm going to send you, there are 3 simple questions. And there is a paper, a very nice one, that you have to read. And it's about phonons. But relax, phonons are nothing else than what we studied since the first lecture. But in a discrete system made by n coupled oscillators. What's next? Just for terminology. If now you play with something that is in a sophisticated word, you can call it diatomic 1D lattice. What does it mean? You consider 2 atoms, like in salt, for example. It could be sodium and chloride, something like that. But 2 masses. One is smaller, the other one is bigger. You could say, oh gosh, what should we do? Nothing more than write the equations, taking care that you have 2 masses, okay? But it's the same. With some algebra, you can write it in a matrix form. You can solve it. You can plug in your harmonic wave, and what you get is this, that is giving this beautiful plot here. Now, you see this equation? You see, if you take the plus or minus, you have 2 names. But relax, there is no strange string theory in 26 dimensions here. No, it's just with 2 masses. If you take the plus, you get this branch. It's called optical branch. You know why? Because actually, for solid state physics, those vibrations that are a little bit higher frequency, you see frequency is higher, are in the optical range. The lower frequencies, the lower branch is like the previous one. And if you go to very low case, it's sound. That's why it's called acoustic. And there is here a sort of a band where frequencies cannot propagate. That's your question. What's happening to frequencies there? It's called the forbidden zone. What is the width of a forbidden zone is decided by the difference between the 2 masses. And just to conclude, I'm going to show to you some animations to which you can give beautiful and exotic names, but actually are nothing else than what we described. But first, let me conclude with this, that if you take the picture, the previous picture, and you consider energy levels at the Planck scale, now you can call them photons. But it's nothing than considering the energy potential, energies that cannot be smaller than the quantum energy. There you can go in quantum mechanics and you will have the full life of a phonon. Otherwise, if you don't discretize energy, they are classical vibrations. Now, final slides. You have seen that in the diatomic lattice, we have two branches. One is called acoustic and the other is called optical. Why? Because one is the optical range, the other can go very low frequency, so until acoustics. And actually, in those situations, we have nothing else than the discrete vision of our two-wave systems that we already studied. Sound, longitudinal, and transverse. Now, how to play with them? Look, we can distinguish between longitudinal vibrations, nice, and if you have two different atoms, you can consider the case in which they are out of phase or in phase. In the other case, you see here, transverse vibrations, and you can distinguish if they are all together or the two masses are out of phase. Many words just to show you this. And that's the end for today. Let's start from the first two. Now you see that all the masses are in blue. Why? Because it's a monatomic 1D, just in one dimension, lattice, because it's discrete. Now the first one is nothing more than just a single line of the animation that I told you was going to be your beautiful nightmare. Where is it? If you take one line of that one, it's this. You can simply draw a line of this animation here, you will get the first. So actually, what we did was much more than the first. But now you can give it a different name. It's acoustic, longitudinal, both. You can do it in a transverse. It's called acoustic transverse. Now with two different masses, and now you see the color here, you can play longitudinal or transverse. In the case of transverse, the masses can be in phase, with two different masses, or out of phase, and you call them acoustic or optical. This vibration here has a higher frequency, it's in the other branch, but they are just names to systems that we studied. To recap, for today we considered periodic functions and their decomposition in basic elements, Fourier analysis. On the other side, we have seen how, starting from basic ingredients, bricks, harmonics, we can write whatever function in that time domain. Then we applied that concept to the initial condition of a string, and we've seen how the initial conditions decide which and the amplitude of the modes that we want to play. Then we've been making a step backward, going back to the discrete nature of vibrations. How much discrete? It depends on the interatomic distance. If we stay with wavelengths that are comparable to the distance, we feel dispersion. If we are living with wavelengths that are much larger than, we're going to k equals 0, everything is going back to the classical relation, no dispersion, omega over k is practically the omega over decay. It's the same. And you can say that phase velocity is equal to the group velocity. Well, you can say that there is just one velocity. But when you feel dispersion, then omega over k is different than the omega over decay. And in some cases, the omega over decay is 0. What does it mean? That the net flux, lateral flux of energy is 0. What does it mean? It's the analogous in the classical world to a standing wave, where energy is localized in anti-nodes, 0 in nodes, and there is no lateral flux. Space and time is separated. Actually, it's a mode of a system. But Fourier told us, look, don't worry, because with modes you can create whatever, also progressive waves, as you have seen in the applet plucking the string. Progressive waves, but written in terms of modes. So today was a strange lecture, going deeper in the classical vision of the initial conditions of the string, right, string, Fourier, and something that is similar but in the discrete version, and we've seen dispersion. And you can call it solid state physics dispersion, Brillouin zones, phonons, acoustic and optical. But from the next lecture, we will forget about distances between atoms, and we will go inside continuum mechanics for solids. Good news, but bad news because we will need to generalize Hooke's law. F equal minus kx is not enough, because force will become stress, displacement will become strain, and they will be two tensors, and they will be put together by a fourth order rank tensor. Bad news, very bad. But for lazy people, it will be short. Okay, so what I'm going to do now is to send you an email with the 3 topics, with a paper, and relax, because I'm waiting for your solutions that you will prepare on a PDF. You can write, you can use text editor, whatever, but please produce a PDF and send it, the answers back to me by email within Monday, next Monday, so you have full of time to do this, and Monday in the morning, so before the lecture of next Monday. Okay? The system should be on. Let's check. Yes, it's on, so you have all the material here. Okay. Goodbye, and see you on Friday. The email has been sent. Close? Yeah. Oh my God. Okay. We have a solution. Thank you.
You can send you the
Pardon?
We can send you the assignment the 23rd.
Yes. As I've been, oh, be careful because it's going. Yes, it's written in the email.
And then, thank you.
Have a nice day, sir.
Goodbye.